Okay. Okay. Let's do this. Good morning. Good morning. Oh, I did this again. Wait, I am actually here. I am actually here. Yes. Good morning. Good morning. Okay. This is awesome. I love this. Sorry, I'm just being silly in a way, or am I? Good morning. Oh, more people coming. Good morning, Sydney. Good morning, Haley. Good morning, Tree. Sorry. Good morning, Loani. Good morning, Sarah. Chat. Oh, more people coming. Uh, uh, good, good morning. Good morning, Pushpita. Good morning, Eric. Good morning, Lena for the double. Good morning, Ashley. Good morning, Erica. I'm going crazy. Wait, chat. Who did I know? Good morning, Sarah. Good morning, Lena. Good morning, Eric. Good morning, Sydney for the double. I think I said. Good morning, Haley for the double. Good morning, Loani for the double. Good morning, Pushpita for the for Pushpita. Good morning and good morning, Eric. Okay, let's get sorry, so oh, more people coming. Okay, hold on. Oh, what happened? 1 second. Okay, and good morning, Monpreet. Okay, so we're all here. I will change the view in a sec. Okay, let's thank you again for like the discussion last time and all that. We're gonna get back to the material now. Oh, good morning, Monpreet. Thank you. Awesome. We're gonna get back to the material now. Yes. And I know that so we're gonna continue with the PDF with the notes that we were doing last time. We'll sort of catch up with ourselves. Um, um, what just happened? Okay. Ooh, I like that avatar. Not that I'm, or am I kick? I don't mean to kick somebody out. Oh yeah, I can kick me out. Right. Okay. Oh, more people coming. Okay. Um, so we're going to right, get back to like math and stuff, but I do want to say quickly again, like thank you for your input and feedback last class. And so I'm starting to upload documents to the Google Classroom in response to your request. Um, um, so where you should look out in general is under the tools. I'm going to switch the screen. Hold on. Okay. If you look in the tools section of Google Classroom, that's where I will put the kinds of things that you're asking for. Um, for example, there is already you may not have noticed already in the tools, there is a sheet of all the equations from last semester that you're sort of expected to know or can use from last semester from Physics 203. And there's also a sheet of all the equations that will ultimately be used in Physics 204. Now, you have to be careful about that because if there's an equation on that sheet but it's on the sheet before we get to it, then you don't want to just take it off that sheet and use it as though we understand it or as though we've established it. You have to be careful about the 204 equations that will accumulate as we go. But the 203 equations, are all fair game. That's number one. But number two, I get, something in the chat. Wait. Oh, good morning, Monpreet, sir. Oh, no, I guess I said that. Okay. But I guess I'll really quickly, I am going to do a screen share for a second. So one, so you asked for one of, at least one of you asked for, can I give like an example of what it means to derive an equation? Um, Now I do feel like, that's sort of what we, in one way or another, I mean, maybe we're all using different words. Probably we're all using different words, but in one way or another, in every math class and in every science class, what we're doing is learning how to derive or prove or establish or show. Like we're learning how to go from something that's known to something that's unknown. Um, I mean, even in a math class where you learn rules and stuff for taking derivatives, still, you're all the time trying to walk through a process of getting from something that's known to something that's um, unknown. What am I trying to say? But I understand that everybody has a different style and a different set of expectations for all that. So very quickly, I want to show you one example that I just made last night for you. Yeah, I'm going to try to do this quickly, but hopefully you see it um, in the Google Classroom. Is this? Wait, can you see this? Yes. Okay. So here's an example by me of deriving a physics equation, deriving a result. Now this is an example of a piece of knowledge that yes, I would like you to have from Physics 203. And yes, I particularly picked this example. I mean, I specifically picked this example because I think it's a good example of how you can get from known principles, laws like Newton's second law to an equation that is not just that results from the application of those laws, and then can be used in other contexts. So this is an example but the derivation embodies such things as making and using a pure free body diagram, and a component free body diagram, etc. I'm going to walk through it briefly in a moment. So I intentionally picked an example to try to address sort of what's a piece of knowledge that kind of I'm hoping we can get up to speed on from Physics 203, but also what do I mean by a derivation? What does it look like? Excuse me. And you'll notice if you look at this, I'll scroll through in a second. There's many ways to do a derivation, like they do it one way in various math classes, they do it a different way in a chemistry class. But here I'm attempting to show you how you might use the 5-step method or to do a derivation. Now, what's the difference between a derivation and solving a problem, by the way? Maybe this is a confusion for some of us, or it's something to be clarified. What the difference between deriving and solving a problem is simply that at some point they become very similar. But when you solve a problem, often that means a particular problem with particular numbers in it, and you get a particular value at the end that relates only to those particular numbers that were given. So the solution to a particular problem is particular. Whereas deriving an equation, it's the same thought process. It's just that we say deriving when in effect we don't have any specific numbers, when we use letters, constants and variables to represent the quantities that could then be generalized, right? So it's called deriving when the answer you get at the end could be applied to any situation of a similar configuration. Now, the truth of the matter is that's more and more what problems end up looking like in physics, and Physics 204 specifically. Like we start with numbers like the mass on the spring, there was a mass of 0.3 kilograms, etc. But as you're seeing, like very quickly, we don't care anymore about that it happened to have had a mass of 0.3 kilograms or a K of 200 newtons per meter. What we're really interested in ultimately in physics is what is the relationship between a given M and a given K and a given X naught or whatever. So this is an example of how you use a 5-step method to derive a equation, like the expression for acceleration down a rough inclined plane. Okay. And so you see 1, 2, 3, 4, 5. I'm doing the 5-step method here. Okay. And what I'm trying to show, but there's no numbers because it's a general derivation. And what I'm trying to show you, so I'm starting with the diagram, etc., right? And here's the question, etc. Like you'll read it on your own, and I hope you do, and I hope you ask me questions about it later. What I'm trying to show here, the main thing is, this is also a self-sufficient document. Like that's why I'm deliberately just putting this in the tools for you to look at later. You don't need to look at anything else to see what this is trying to do. It's setting you all up from the beginning and getting you to the end all on this piece of paper, on this, document. Um, um, what's my point? And even like at the end, when it circles the answer, it's making it clear that that answer is a full statement that relates us back to the original question, the thing we're trying to prove, like up here based on this diagram. Okay, now, um, what am I trying to say? And and I made the obvious, whatever. I wrote this 2 nights ago, so you could see, and hopefully it's clear, and comprehensive. Now I'm going to put another example later because one thing about this is because this is me, and I've been doing this for a while, whatever. Like it looks very formal. I'm not saying you always and you may not even want to read this. It like looks like a textbook. I mean, it's not, but it looks like it could be a textbook, which means that some of you might not even want to read it. I understand that. Um, so in 2 nights or soon, I'll put another example up where I'll do it in handwriting with different colors and stuff and make it look more like maybe you would make it look, which is fine. Um, but even there, even if you're doing it in handwriting with different colors and stuff, there's a way that you can get the whole thing across. Notice one aspect of this style, even this sort of textbooky style, is that I'm going from equation to equation to equation to equation. Well, and I'm based on that. Well, here we go. Like equation, all to get to a final answer equation. I'm even like numbering my equations as I go. But as I go through each equation, I'm talking about what I'm doing, right? Like now I'm doing it in my style, right? I mean, it's like, and this is like a standard formal style. Like obviously this could be like in a journal, which is really our ultimate aspiration. That's one of the reasons I put this here first. I mean, this is the ultimate goal. So I'm talking through in paragraphs of English and introducing each new equation as I get it. And all of them, they're all based on the assumptions being made in step 3. So I'm talking through the equations as I go. Now, another way to do that, and this is a standard style of like paragraph of English, then centered offset equation, then paragraph. But another way to do it, which is lovely, and which I'll show you, is by handwriting to have like equations and then have the English annotation, and then have arrows and stuff like equation in the center, arrow going off to the right with English there or different colors. Like obviously you can make this much more inviting to the eye or make it much more your style. But the point is you got to talk through the reader from beginning to end. So all of this is meant to demonstrate to you what I mean by a self-sufficient document, what I mean by a derivation, what I mean by the 5-step method. This is a formal example because it's like the ultimate goal. And because it's just like the way I think these days. So I'm going to give you a less formal example in a couple of days. You could pick your style, do it, develop your own style. But all the elements that we're looking for are here in this example. All similarly, or also I'll say the other example that I'll put in, and maybe I'll put many examples, but the other example I'll put in a couple of days will be more of current material. So hopefully you get, different. So this is like older material, but that will be newer material. And hopefully that's helpful. So please look at this on your own later, go through it, ask me questions if you have, and yeah, just that. Okay. So, but hopefully you might also, I'm talky, as you know, I'm going to switch the subject now and get back to the math, but I'm also secretly doing this. I'm over explaining some of the equations in here, partly to emphasize to you that you should also over explain. It's all about over explaining, but secretly also, I'm hoping maybe if those of you who weren't totally comfortable with either Newton's second law or free body diagrams, maybe you might learn something, like it might help you. It's meant to also like help refresh you on that. It is a little textbooky because but that's what it is. But I should also say if it sounds or looks textbooky, that's because that's me, and I use, the writing program. If you're interested, I mean, the writing program I use makes things look like a textbook. The writing software that I use makes things look, but what I'm really trying to say, how can I put this? Like, you don't want to sound like this. You don't want to sound like AI when you write to me. You got to write in a way that is your voice. Like, it's clear when someone's writing in their voice or not. Like, and if you look at this closely, you'll know it's me. Because I'm over explaining stuff in the way that I do. And that's what yours should, it should be clear that it's you. And believe me, I've been poking around a lot on AI, but like it's fascinating, all that. But like it's so clear the difference. It's clear. I'll just leave it at that. Okay. So I'm going to stop the screen. Oh, there's something in the chat. I'm sorry, but I'm going to stop the screen share. Oh, yes, that right. Very good, Fabricio. Correct. I use latex. That's why this, for those of you, so latex is like the standard professional way of like writing mathematical documents that intersperse equations with um, English. So yeah, and I am not saying you guys have to do that. On the other hand, if you're trying to go into science, and part of where we're trying to prepare you here is for like a career in research or et cetera. So it's something to aspire to. And I would be happy to help any of you individually if you're interested. I'm glad Fabricio recognized that. I wasn't sure if guys were aware. It's something very much to be aware of. And this is not a paid advertisement, but yes, it's latex, but that doesn't mean that I'm perfectly fluent. Like, it means I use the free online web, what do you call it? The free web application called Overleaf. This is not a paid advertisement, but as an academic to you guys, if you're interested in all, I would highly recommend that you check out the website Overleaf. It allows you to write in this way and do equations and diagrams. Oh, and the diagrams I made, again, this is not a pay. I'm serious. It's not the diagrams I made, but I made on Google Draw. It took I did this on purpose in response to your request. Like the other night, I started it 2 nights ago and I finished it last night to show you it doesn't have to, this is, I think this is pretty extensive. I'm kind of proud of it actually, but it doesn't have to be like a month-long undertaking. I just did the diagrams in Google Draw. So you can do that too. And of course, Adobe Illustrator is like even better if you really want to. But whatever, Google Draw is free, and you can do stuff like that. Okay, so. But yes, Fabricio, good call. And if that's something you know how to do, I'd love to hear like privately, or if you want to know more about, I'd love to talk to you about latex, Fabricio, and anybody else. But yes, so that's this. Okay. But this is also just my way of saying I hear you guys. I'm taking your request seriously. This is the first of and the equations are in the tool. So I'm not done yet meeting your request, but just so you know. All right. So I'm going to stop this unless there's more questions. What am I doing? Oh yeah, I'm stopping. Stop the share. Okay. Okay. Now I'm going back to the board. Yeah. Wait, how do I? Yeah, can you see? No, you can't. Hold on. You can just see my ceiling. Hold on. Oh, share. So also tell me if there's something, if you wanted to ask, and if I'm missing, but okay. Okay. So we're here. So this is today, it's the 26th, right? Okay, so I believe that, so I'm back to this is like back to the notes that we were doing 2 days ago. So I think this is where we ended. Stop me if I'm wrong, but I think what we just ended with was the right-hand rule, which is the convention that allows you to get the direction of the cross product. Because again, quick sum, the dot product multiplies two vectors in a manner that produces a scalar, but the cross product is an operation that allows you to multiply two vectors in a manner that produces a vector. Okay, sorry. Right. Okay. So the answer to a cross product doesn't just have size, it has direction. So we need a way of knowing what that direction is. And the bottom line is the direction of the answer to a cross. The bottom line is that the cross product always measures how perpendicular two vectors are. So the answer will be perpendicular to both of those vectors, i.e., it will be perpendicular to the plane in which both of those vectors were found. So the only question is whether it pops out, the answer pops out of the plane or into the plane. And so when it really comes down to it, so just use your right hand. I mean, really the simplest thing to say is if here's one vector and here's the other vector, then the answer will be my thumb. I mean, maybe that's simpler than all this other nonsense I'm saying. But you'll know you're doing it right. You'll know you're doing the cross product correctly if you find that reversing the order of the operation flips your answer to the opposite direction, right? I mean, and I'm going to move on, right? Like this crossed with this direction where my my first finger is pointing, crossed with this direction, gives me my thumb. But if I did it the other way, if I did this vector first, I would literally have to do it the other way. I would have to, like, if I'm going down first and then over, I'd have to go down and then over. So my thumb would point back the other way. I didn't even say that right. I mean, I didn't say that smoothly, but okay, I'll leave it at that. All right, now I'm going to move on. I'm going to change the view of the screen. So I'm moving on now, unless you stop me. And I'm moving on to say more about vectors and specifically about the dot product and the cross product. I'm going to say more about vectors now, but I'm saying stuff that you didn't need to do that math 2 part 3. Like what you needed to do the vector stuff in homework 2 was just what I've already said and what I had said last week. Now I'm launching off to go deeper into vectors. Okay. So, and also again, reminder, because so you all did that homework. Most of you gotten it back. No, all of you have gotten back, except I think one person who, I'm going to walk through that homework and you will, again, if you got it back and if you got it back already, you did get it back. If I'm just trying to make it clear again, I think you know this. You can still revise and upload and get the rest of the points. If you got more than 50 points, you can get all the rest of the points. If you got less than 50, maybe you can't get all, but you can still get a bunch. But you do, but I am going to start walking through it when I'm done with this vector stuff. I mean, next week, I'm going to start walking through it. Actually, so you can see literally specifically what I was looking for and you can revise according to that. I want to say before I forget, the homework that's due this Tuesday, it does not involve any of what I'm saying right now. It will be a big break to many of you from homework 2. Like it's shorter, it's less involved. It's just, if you understood kind of what was going on with the derivatives, it's just about the derivative piece. So it's not new material. I'll just leave it at that. But still, even if I don't provide you with a diagram, you've got to provide me with a diagram. No matter, like that's the first place that maybe people you want to revise your old homework. Like you need to always provide a diagram, especially when the question didn't provide one, so that we can all right, I think you get that. But I'll give you more specifics when I go over it on Tuesday. All right, so now moving on. I am moving on. I want to introduce a concept called a unit vector. Okay, so from now on, given any vector, call it vector A, any random size and directions, and any random arrow, if you take that arrow and you divide by its own length, I mean, again, remember, if you put an arrow over a symbol, that means you're referring to the whole vector, the magnitude and the direction. If you just write the symbol without the arrow, you're not making a typo, hopefully. You're referring only to the actual size of that arrow. So from now on, if we take an arrow called A, a vector called A, and we divide it by its own size, we get a new vector that is designated with a caret above the A, and the caret that punctuation mark called a caret. In physics and in math, we call that a hat. I know that's really silly, but we do. We call it a hat. So from now on, a hat is by definition is defined to be a arrow divided by a. What does that mean? It means that a hat from now on is the vector divided by its own size. And we're going to call this, so we read it as a hat, but it's called the unit vector for a. Example, if we have a vector that's 3 miles pointing to the northeast, the vector A is 3 miles of displacement pointing to the northeast. The unit vector of A would be that we take the 3 miles to the northeast and we literally divide by 3. We just divide by the length. So what we will have is 1 mile to the northeast. That would be called the unit vector for A. It is a vector that is defined to point in the direction of A, but have an identity, like a size of 1 unit. What's the point of this? A good question. Well, remember we said before that whenever you take a vector and you multiply it by a scalar, you get a new vector. And then I think I hinted 2 days ago that, in fact, that's not only is that something you can do to vectors, but in a way, it turns out that's the way we want to sort of go backwards in our mind and think of vectors in the first place. Like once you define a unit vector, so a hat is a vector with a size of 1. Once you have that concept in your mind, you can just multiply both sides. I'm looking at the bottom in yellow here of the screen. If I multiply both sides of the by a, then what I'm saying is, from now on, I can think of the vector a as a raw size multiplied by a raw direction. In other words, if someone says the vector, if I say, how do I go to the post office? They say, I'll tell you the vector that gets you there. You're going to go 3 miles to the northeast. What I can really think of in my mind is, and it turns out to be advantageous to do this, I can first think of, I could think of it as, or I could think of the following, or maybe they could even say, maybe this would be better. Imagine if they said, okay, what you're going to, I'm like, how do I get to the post office? How do I get to the post office? And they're like, calm down, yo. Okay, first of all, the post office is over there to the northeast. You're going to have to go to the northeast, okay? I'm like, okay. I thought it was over there. Oh, it's over there. Okay. So they're like, you're going to go to the northeast. So they say that. And then they say, and you're going to walk about 3 miles to the northeast. So in other words, imagine that we always give direction first. Imagine that the way we think of vectors is we first think of a unit vector that points in a particular direction. Like we think of a mile to the northeast. And then, so we think of an arrow of length 1 pointing in a particular direction. And then we scale up that arrow or scale it down by a certain amount. So we think of a hat and then multiply it by a when we're trying to consider the vector a. I see something's in the chat. I'm going to shut up. It probably means I should shut up and move on. I think you get it. But from now on, we think of a given vector as a unit vector pointing in a particular direction, scaled up or scaled down by a certain size. Okay, I'm going to look in the chat. Sorry. Yeah, fair enough. I think that was the example. Okay. Yeah, hold on. I may have an example right here. 1 second. Yeah, okay. An example, sure. So this is kind of the written version of what I was just saying. And if it seems kind of like it is a simple idea. It's not meant to be very complicated. It's just like super useful. So this, but thank you for asking me for an example. Here's the example up in white and red, is that if you have this vector A that's 3 in a particular direct, let's even be more specific. Let's say, can I do this? Well, yeah, that if you have a vector, the red vector A, that's pointing in a particular direction and has a certain length, let's say 3, what I'm saying is first think of a smaller vector that has a length of only 1, but definitely points in the same direction. Like I'm deliberately making those two arrows parallel. I would put a little theta, you could put a theta on both. Well, I guess it's going to get too crowded. But like, so the idea is, how do you think of A from now on? A arrow, you think of it as a hat, a 1 unit length vector pointing in a particular direction, and then you multiply, you stretch that small arrow by, in this case, 3 to get the big arrow. Oh, you can't see what I wrote? Wait, can you not see the screen? Wait, you you can't see the white and the red. Hold on. Wait, there may be a problem here. Wait, can you see the, well, I'll wait. Sorry. Yeah, it's in the, okay. And yeah, no, it's very fair that you're asking for a visual example. I could stop the presses and make a big picture out of it, but I think I hopefully that small picture does it for you because it's a big deal, but it's not a complicated idea. We're just saying from now on, a given vector is a pure direction times a pure size. Okay, I think okay, yeah, no problem. No, but thank you. And I'm gonna keep going because I think that'll probably do it for you, but I like the request. I mean, okay, so what is this? Um, so now I'm gonna go a step further, and there will be more pictures of this. Now I'm gonna say, okay, look, so from now on, vector B can be understood as B times B hat. Vector A can be understood as A times A hat. So this is just another way of saying, instead of constantly using English to say a vector has a size and a direction, it's a way of packaging all that English into just a simple math expression. It's just saying a vector is literally a multiplication, a monomial of two terms, a pure magnitude times a pure direction. Like that's what we're saying from now on. But here's the catch. That's good. That's a good start. But that means now, like we've got vectors pointing in different directions, and they're hard to relate. If the direction of A is the direction A hat, and the direction of B is the direction B hat, like how can we combine or relate these two vectors to each other? So what we do is we back up and say, oh, well, look, no matter how many different directions you're going, say you're in Manhattan, even though one person has to go northeast and another person has to go southwest, we're all in Manhattan. We're all in the same grid. We all follow the same rules of thinking everything in terms of X and Y axes, right? And literally Manhattan's a perfect example of this. Like, even if you have to get northeast, the way you get there, the way you do it is you have to walk a certain number of blocks a certain number of avenues cross town, and then a certain number of blocks uptown or whatever, right? Like you always end up thinking of what you're doing as a sum of some amount up or downtown plus some amount crosstown. Like, right? Even if you're taking the subway, like you know what I'm saying. So in the end of the day, we think of everything in terms of these axes. This is back to Galileo. So we pause and we take this unit vector concept and we say, you know what? The directions X and Y, and if we're in 3 dimensions, Z, are so important. And once we pick a coordinate system, everything is relative to the X and Y and Z axes. So let's stop before we go any further and establish the unit vector that points along each of these special base axes and actually give it its own special name. So it says here, then from now on, we can assign unit vectors to the three directions of a 3D coordinate system. We're moving into three dimensions now, right? Because the cross product brings us into three dimensions, so that all other directions can be expressed relative to these. So here's what I'm saying. Okay, here's an example now. So I'm saying from now on, if you were to walk along the x-axis 1 unit along the x-axis, like that's such an important idea. Walking along some x vector divided by its own length would give you a unit vector along the x-axis, what we would call x hat, like based on everything I was just saying before, just like whatever, just like a unit along whatever directions A is pointing in, we would call a hat. Well, if you walked a unit along the x-axis, we would call that x hat. But it's so important. Everything else is going to be written in relation to x-axis so frequently that we give it its own special name, and we call it from now on I hat. Like I'm saying that's an I. My handwriting is this. This is an I. This is supposed to be an I with a hat above it. Okay. And I'm literally, I want to, this is not something I'm assuming you know. And I didn't assume you knew it to do the homework, and you didn't need to know to do the homework. But I'm telling you now, I'm defining from now on, I hat means the unit vector that points along the x-axis of whatever coordinate system you're in, whether your x-axis is like tilted on a plane or horizontal, like wherever your x-axis is. If you walk 1 unit along that axis, we call that vector the unit vector I hat. Similarly, if you walk along the the y-axis 1 unit, we call that j hat from now on. This is not me, like this is, you could look it up. It's standard in math and physics to do this. It's all over web pages, whatever. And if you walk 1 unit along the z-axis, we call this k hat. So the three unit vectors from now on, the three base unit vectors that sort of define our motion throughout a 3D coordinate system are called I hat, j hat, and k hat. Okay, it's a definition. It's to make our life easier from now on. What do we do with this? Okay, this gets a little now. What I'm saying, and I'm thinking, was tree? Yeah, the tree was public with that. Okay. Oh, wait. Oh, sorry. Oh, sorry. There's a question in the chat that I missed. Hold on. I see that there's a direct question in the chat that I missed. I'll get to it in a second. I apologize. Sorry. Wait, I'm just pausing on this question in the chat. Okay, there's only one question in the direct chat right now. So you know who you are if I'm talking to you. That's a really interesting question. I would like to talk with you about that individually later. Again, you know who you are because there's only one right now. I hear you, and I would like to expand on that later with you. I mean, the simple short answer right now is don't worry. I mean, it's okay, is what I'm saying. But I would love to have a longer discussion with you about that. But yeah, I see you. I mean, I understand what you're saying. Okay. So back to this now. Um, um, this is a little complicated. I mean, and the picture's a little complicated. So bear with me. What I'm trying to say is, on the one hand, any vector A could be viewed as a certain length in a certain direction, the direction A. But again, picture the Manhattan example, or picture physics 203. If you were somewhat, picture like lab number 3 of physics 203, when you were drawing on the graph paper, when you first looked at what turned out to be vectors, what you find is that any vector in a coordinate system can be understood as the tip to tail sum of its constituent components, right? This is also like the mg sine theta, mg cosine theta idea, whether it's displacements or velocities or forces or accelerations. The idea behind vectors is that to go northeast is really to go some amount east and also go some amount north, right? To go some amount east and some amount north simultaneously, well, or, together, but independently, right? Um, so if I go off at some angle theta, I'm really going some amount over and I'm going some amount up. I'm going some amount over the x-axis and some amount up on the y-axis. Each of those legs of that right triangle are themselves vectors, right? If I'm careful with and I draw arrows and I put the arrows tip to tail, I'm saying this plus this equals that. Meaning if you want to get to that point up there, you could walk this way first and then walk that way, and you would land at the same place as someone who just walked like that, right? So this plus this equals that, plus in the vector sense, right? So the a sub x vector plus the a sub y vector equals the a vector, and we've always believed that in physics 203. You might want to tell me if you're not that comfortable with it, but it's like true. So now what I'm saying is, okay, let's use our new notation to re-look at that. The ax. So I'm saying I'm here right now. Well, I'm here. I'm saying any random A vector can be actually broken up into two pieces that lie along the same axes as any other vector, right? Like, what's special about X and Y? The fact that every other vector, B, C, D, E, they're all using X and Y as well. So I can rewrite vector A as the sum of vector A sub X plus vector A sub Y. But now, with our new notation, each of those individual vectors, I'm now going down here, the vector A sub X is really some amount along the X direction times the unit vector pointing along the X direction. So be careful. Like, this is like a subtle change in notation. What I'm really trying to say is the vector A sub X with an arrow over it, that's not the same thing as just writing A sub X. A sub X is the length of the vector A sub X with an arrow over it. The entire vector A sub X with an arrow over it is some amount AX times the unit vector I hat. Like imagine you walk one unit along the x-axis and then stretch that walk out by an amount AX. That gives you how far and where and in what direction you walked along the x-axis. So I'm saying from now on, in 2D, you could say a vector A could be written as a sum of products or a sum of monomials. Looking at the time. So leap number 1 of today was that from now on we could write a vector as a monomial. Like, leap number 1 of today is we used to say a vector in English is magnitude and direction. Now I'm saying you don't have to say that in English anymore. You could literally say it's magnitude times direction now if you define these things called unit vectors. So leap number 1, or like new idea number 1, is a vector can be written as a magnitude times a direction. How do we write the direction? With a unit vector. Now I'm going a step further and saying, but you know what? Yes, you can do that. But even better, you can view any vector as the sum of component vectors, each of which lies along a base coordinate axis. So from now on, vectors can be written as sums of products. The vector A, and that gets rid of all the English, which is sometimes a good thing. The vector A is from now on AXI hat plus AYJ hat. That's what I'm saying. And then I'm going to go a step further and say, now that we're starting to deal with 3 dimensions, if I'm in 3 dimensions, I would say from now on, the vector A is AXI hat plus AYJ hat plus AZK hat. It's like a lot of new notation, but it's just saying how Where I walk in some cube is how far I go along the latitude, plus how far I go along the longitude, plus how far I go along the altitude or whatever, right? So, okay, so that's vector A from now on is written that way. So what? Oh yeah, I think these pages are out of order because but I already said this. So the point is now A and B can both be written in terms of I hat, J hat, and K hat. So they can be related to each other. Oh, yeah. And this is all still saying the same thing. I'm going to move on and say, but again, anything, if you ever remember anything from last semester about like, oh, like this component is like, this component of the vector A would be like A cosine theta. Yes, you're right. Like if you're remembering cosines and sines matter, yes, you're totally right. And that's still true. I'm just trying to reinforce right now that those things that you would get last semester, like V cosine theta, that's the magnitude of Vx. The direction of Vx would be I hat. Like that's all. Okay. So yeah. So this is what I just said. Now, now I'm going to turn it to you. Now we're going to do some exercises with this examples, like again, like Trias, which I appreciate for like a concrete example. Here we go with now some concrete exercises and examples, and you're going to do them in the private chat, in the direct chat. I'm asking you right here on the screen, and please again, the direct chat, not the public chat, for your sake and for mine. I'm gonna ask you. It seems like a random, it seems like an out of nowhere question. It may even seem like you don't have enough information, but you do. I want to ask you, what is I hat dotted with I hat? Like, what's the dot product of I hat with itself? Now, you'll know what you need is a definition of dot product. Like, so turn the pages back to where we established that like last week and last semester. What is dot product? How do you do it to two vectors? And then what's the definition of I hat? I'm going to remind you right now, I hat is a vector. It has a certain magnitude. It's a unit vector. It's the unit vector that points along the x-axis. So it has a certain magnitude, which is the same magnitude as all unit vectors. That magnitude is 1 by definition. And has a certain direction, points along the x-axis. So I want to ask you right now in the direct chat, I'm going to shut up. Can you please give me an answer, a numerical answer to what is I hat dotted with I hat? And then also, second question, what is I hat dotted with J hat? So please do these in the direct chat. I won't wait till I get everybody, but I'd like to get at least 3 responses in the direct chat before I move on. So, or just tell me in the direct chat, I don't know what's going on, or like I need you to repeat or something. But please, in the direct chat, answer. Okay, cool. I see one person in the direct chat. Thank you. That's awesome. By the way, I now see 3 people in the direct chat. That's great. And for what it's worth, the first 2 people that I just saw are totally correct. So that's awesome. I'm not saying that to scare anybody, but that's great. So people are with me. So 3 people are correct so far. That's all. Okay, fair enough. And I'm getting an honest expression of not knowing what's going. Okay, and I see someone just corrected themselves. Okay, but I see the honest expression in the. Great. I'm going to wait till like 2 more responses, then I'm going to do it. I mean, if you're confused, so at least one person or 2 people is saying they're a little confused. So hopefully I will clarify in a minute when I go over it. Um, Okay, now I'm getting a bunch of it. So again, by the way, all of you should submit for points. Like you're participating. Like thank you, and it's helping me help you. And I'm going to go over it in a second. I'm not going to leave you dry. But remember, you should submit for points no matter what. But if it turns out that you got it wrong, don't be ashamed of yourself. Be proud of yourself for participating. And remember, there's a portal where you literally can submit for points just for the fact that you were wrong about something. Like it's a reward for trying. So, because I'm about to say, I'll say the answers good. And I'm seeing, like, and look, I want you to know a lot of these answers in the chat are right, but some of them are wrong. And some people are admitting they're confused. So you're not the only one, whoever you are. If you are wrong or you don't get it, you're not alone. It's okay, but we can all do better if we all come together and you know, okay, but I'm seeing a lot of answers. Great. I'm going to tell you. All right. Yep. Oh, well, here you go. Yeah. So here's the answers. And I will tell you, I'm going to explain it now. But yes, I agree. The answers are to the first one is one, and to the second one is zero. Like they literally are the answers are one and zero. Why? Because, so very good. So why? Because to do the dot product of two vectors, if you take the definition from last week, the dot product, sorry, does that work? Sorry. The dot product of two vectors is the magnitude of one vector times the magnitude of the other times the cosine of the angle between them. Like that's the definition. That's why I'm using a triple equal sign. So I wrote it out. But what is the magnitude of each vector here? How could we possibly know? He's just saying a random letter, Yaverbam. He's just saying I. Well, you know what the magnitude is because I put the caret above, the hat. Once I put a hat on a vector, that means it's a unit vector. And the magnitude of any unit vector always, by definition, is one. Like that was what Tree was asking about before. The unit vector of anything is you take the vector and you divide by its own size. So you always get a new vector that points in that direction and has a size of one. I, J, and K are unit vectors. They just happen to be the special base unit vectors that point along the pure X direction, the pure Y direction, the pure Z. What makes them special is they point along coordinate axes, but they're still unit vectors. So they have a size of one no matter what. So the size of I hat is one. The size of it again is one. And then I'm doing the cosine of the angle between the two vectors. What the two vectors are one and the same vector. It's I hat dotted with itself. So the angle between any vector and itself is zero. Yeah, the same vector must be parallel with itself. So the angle is zero. So I hat dotted with I hat is 1 times 1 times 1. That's the answer is 1. So any of you got it right is good. And if you're following the logic, and you'll tell me in a second if you're not, if you're following the logic, that would mean any unit vector. Yeah, certainly any base unit vector, but any unit vector at all, if you dot it with itself, you'll get the answer 1. It's always true from now on. Now, again, this is an example in a way, you can memorize that if you want. You can memorize that I hat dotted with I hat equals the same thing as J hat dotted with J hat equals the same thing as K hat dotted with K hat. You can memorize that it's all one, but I would say no, better to derive it. I mean, better if you get the concept, if you get you could turn this in as a derivation. If you know the definition of dot product and you know the definition of a unit vector, then it has to be the case that any unit vector dotted with itself from now on is 1. Okay, but yes, that is what I'm saying, person in the, sorry. Wait. This is 2 cool things in the direct chat. Right. Okay, I'll just read these out loud. I'm not going to read the names, but but I'm also going to say that I'm getting a variety of people in the chat, which is great. So I think we're all coming together more. One person saying, "So is this a concept rather than actual calculations?" I mean, that's a really interesting distinction. Maybe that's like what I'm doing. I did calculations. I'm doing an example. I'm doing calculations, but right, I'm doing calculations based on these pure definitions that I just gave you. So the answer that I'm getting to these calculations is not just a random example. I mean, it is an exercise for practice, but you're right. What we're getting here is now a concept. I mean, we're using a concept, but we're getting a concept. Like the concept we just discovered in doing this exercise is that from now on, if you dot any unit vector with itself, you'll get the answer 1, like always. So yeah, it's a concept now. And I'll go on, and maybe I'm misunderstanding that question, but I want to say maybe that's a really good question. Maybe that is the thing that's sort of new to many of you, or that I want you to get used to, is this is the way physics really works, is we get a concept, like we started at like a place, like a definition or a law. Then we apply that definition or law to a problem, to a specific problem, but usually the specific problem that we apply to is really not that specific. It's usually we apply to a problem that represents a whole category of related problems. So then when we solve that problem, now we have a new result or a new concept or a new equation that then we trust from now on for all future problems. So it is true that every time we solve a problem in physics, we're really doing a little mini proof or a mini derivation and building a result for the future. That is the way physics works. And maybe that is what, and that's why I'm going to move on. I know it drives people crazy but I'm trying to figure out like what is the disconnect? Because obviously was a disconnect somewhere. I think that's why physics looks intimidating all the time. Why it looks like we just have so many equations and you never know what to memorize and what not. And and it seems like it goes so fast. And yeah, that's all true in a way, but like really what we're saying, we don't want you to memorize all these. Every time we solve a new problem, we're getting a new concept for the future. And we then use that in the future, and we sort of hope that by practicing it, we get more used to it. But all of this stuff is derivable. So we're not expecting to memorize all these. I don't know, I'll go on. But yes, this is a concept now. I mean, I'm glad you asked that. And you should talk to me privately too for more development on this if I'm not being, but yes, it is now a concept that any unit vector dotted with itself is equal to 1. But we just found that out. I'm not just telling you. I think we just sort of proved it by doing that exercise. Okay, then there's another question in the chat. Yes, I hat dotted with I hat is always equals 1, now I'm saying. And that means if you get the logic of it, I mean, also, maybe this is what's hard about physics. I just did the example I had, but I'm saying if you watched the example or you did it yourself and you saw the logic, then it has to be true for j hat as well and k hat. Like that's where it becomes a concept because I just represents unit vectors in general. All right, I'm going to move on. I think you get it. But all right, so from now on, unit vectors dotted with themselves yield 1. But now we go to the other example. I'll be quicker now. What if you take a unit vector and dot it with a different unit vector? More specifically, what if you take a base unit vector and dot it with another base unit vector? What do I mean by base? I mean a unit vector that lies along a coordinate axis. The coordinate axes unit vectors have these special names, I, j, and k. They are special, useful unit vectors, and they are along the axes of space. However you're defining your coordinate system, and again, this is part of why the example that I gave you in the Google Classroom is about an inclined plane, because the inclined plane is where we first get used to the idea that you can choose your coordinate system. You can tilt a coordinate system, and you should, to make life easy in physics, and you're allowed to based on Galileo. But when you tilt a coordinate system, you tilt the whole thing. It's still a coordinate system, right? And so X and Y and Z are still perpendicular to one another, and everything is still in relation to them. So we give them these special unit vector names, I, J, and K. And now we see what would happen if you do the dot product of I hat with J hat. Well, it would be, again, excuse me, 1 times the cosine of the angle between them, but now the angle is 90. How do I know? Because it's the coordinate axes, all coordinate axes, x, y, and z. The one thing that makes a coordinate axis is that it's at right angles to every other coordinate axis. So the dot product of I hat with j hat has to be 0. And if you follow that logic, that I hat dotted with j hat has to be 0, then that would be true for any two unit vectors that are base unit vectors that aren't the same. J times K, or I mean, J dotted with K hat, or I hat dotted with K hat. They all have to equal 0. Okay. So that's a concept. That's that exercise. Now we still have 15 minutes for good or for bad. And so if I'm yelling, it's probably just because I'm excited. I'm not angry. I'm not. I'm not. No, so let's move on to cross products. Now, this is a little trickier. Stay with me. The cross product is the same kind of thing, but now we're measuring perpendicularity rather than parallelism. And now we're producing answers that are themselves vectors, not scalars. So I'm going to pause. I'm going to ask you to put answers in the direct chat to these 3 questions. I hat cross I hat cross J hat, and I hat cross K hat. I'm going to remind you of a couple things, and I'm going to shut up because I want to see in the direct chat. Uh, First, you do the same, follow the rules. Take the definition of cross product that we established last class. Take the definition of each of these unit vectors, apply, kind of like we just did, 5 minutes ago. But remember a couple things. One, your answer is going to be a vector, not just a number. If you think you're doing something and you just get a number, what you may be right about that number, but that number is just the size of your answer. Your answer also has to have direction now because it's a cross product. Cross product is a little richer than the dot product. So number one, your answer has to be a vector. Number two, just a reminder, remember the cross product. And to get the direction of your answer, you're going to have to use the right-hand rule. So you're practicing that. But also remember with the right-hand rule, the cross product is anti-commutative. So if you go in one direction, you get a certain answer. But if you go in the opposite direction, you'll get the negative of that answer. Just remember. All right, I'm going to shut up. We have 13 minutes. I would like to know in the direct chat, please, as it says in blue, in the direct chat, can you please give me your best thoughts that I hat cross I hat cross J hat, and I hat cross K. And again, to the person that asked before, like, yeah, this is an exercise, like this is an example we're doing, but it is not a random example. Like whatever answer we get here is then true forever. So it becomes a concept. I'm sort of really intrigued by that person and I hope you submit for points for that. And you may want to tell me more later what you mean by concept rather than calculations. But bottom line, when the person used the word concept versus calculations, I feel like in my mind, that's like derivation versus problem solving, which I think is what is like, bothering some of you. So, yeah, that's what I'm trying to lean in here. And maybe you really, please do look at that document that I just put in Google. The difference is just whether it's particular values or general relations. But all right, I'm shutting up. All right, direct chat, please. Okay, that's one person in the direct chat. Thank you. Awesome. Oh, nice. Oh, nice. There's one. Wait. There's one person in direct chat, and I love a lot of what of that person's saying. And to be really frank, I agree with 2/3 of it. And then there's like one little piece I don't agree with. But no, that's awesome. And please submit for points. It's one person so far, so you know who you are. But please, let's go, people. I don't mean let's go, but I do mean, or But and I want to emphasize anything you need to do this. I'm asking you to do an exercise and I'm asking you to stay with me as a class, but I'm also asking you to do something based only on what we're saying in this class right now. It's not based on anything from last year or last semester or anything like or calculus class. I'm asking you to like lean into a concept that I'm explaining today. So I think so nobody's at a disadvantage. You can do it if you've been with me today. But there's only one person in the chat, so that's a little disturbing. The, oh, good. Person who just changed their mind. Awesome. You changed your mind on exactly the right thing and you changed it correctly. Thank you. That's a conversation right there. See, that's worth 75 minutes just to have that little moment. Seriously, please submit for points. And by the way, a lot of these people that I'm talking to individually are different people, which I appreciate. Like whoever I'm talking to individually it's not the same person this whole period, and that makes me very happy. Okay, so now I'm getting more in the direct chat. Thank you. Here, wait. Yes. No, person who's saying that they are confused, I think that person is getting less and less confused because their first answer to the first one is correct. So even though they're saying they're confused, and I appreciate the honesty, I think they're getting less confused. So that's great. Another person in the chat, yes to the first answer, yes to the second answer. Awesome. And you didn't put the third answer. That's fine. The third answer is the hardest. So great. And that's a totally new person too in the chat. Or no, it's not totally new. No, you've been with me. I'm sorry. But like I'm loving the variety here. So yes, person who just put two answers in the chat, you're right. And person who thanked me for thanking you, awesome. I'm gonna wait for a couple more people. The question is these three exercises at the bottom of the sheet, like put in the direct chat, or even just honestly say, I've been spacing out, but I'm back now. Like, I understand. Look, I sit in faculty meetings on Zoom. It's torture. I know. And it's easy to leave and think you'll watch the video later, but like, but come back. Oh, great. I see another thing. Okay, fair enough. I appreciate the honesty. I'm unsure how to approach. Okay, I will show you in a second. Now I see other things in the chat, and I will shut up now that I'm getting like a majority. Person in the chat. Okay, and now I'm also getting some answers that show that you're paying attention and show that you're with me, but I don't totally agree with. So I will talk about it in a minute, but that also shows we're getting our money's worth. Oh, interesting. Okay. Nice. Awesome. Okay. I see all of you. And we have 8 minutes left, so I'm going to do it now. And there's enough variety here that I think it's worth me doing. I will say about three of you put in that the answers were 0 and then 0 and then something. There's no way you would say that unless you were sort of paying attention. Like how could you make that up? Like if you put like, wait, no, sorry. I mean, no. I take that. Some people are putting answers like 1 and then 0 and then 0. That is really. Wait. That's smart if you're putting 1 and then 0. But number one, that would be like dot product. We're doing cross product now. And number two, I'm going to show you now your answers can't just be raw numbers. They actually have to be vectors. Although if your answer is 0, okay, that means 0 magnitude and 0 direction. That can be okay. But once your answer is like a 1, it means it's got to be something else as well. All right, so I'm going to do it now. So there's enough here to show me that I need to do it. So here we go. If we're doing I'm doing the first one. Yeah. I'm doing I cross, but if you wrote I'm sure how to approach, that counts as participation. You should submit for points. Okay, you get it. I cross I hat. I mean, I hat cross I hat. Well, to get the magnitude of it, to get the magnitude of the answer, according to the definition from yesterday of the cross product, you would do the magnitude of one times the magnitude of the other times the sine of the angle between them. Like now we're doing sine because now we're doing cross product. We're looking at how perpendicular two vectors are. Okay, so you would do the magnitude of one times the sine of the other. Well, the magnitude of each one is 1. I think you're getting used to that now. These are unit vectors. The magnitude of each one is 1, no matter what. Now, if it's the same vector with itself, the angle is 0, so the sine is 0. It's not perpendicular. No vector is perpendicular at all to itself. So the cross product of any unit vector, in fact, any vector the cross product of any vector with itself is going to be zero. Technically, the zero vector, like something with zero size and zero direction. So the answer to, and some of you, yes, yes, yes. Okay, sorry, pause. Someone in the chat. If you're understanding correctly, the cross product always takes sine, yes, and the dot product always takes cosine. Yes, because sine measures perpendicularity and cosine measures parallelism. How do I know that? Because the sine of zero is zero and the cosine of zero is one. So yes, good question. Yes. So the cross product of any vector with itself is zero. A vector is never at all perpendicular with itself. Okay, but then we go to the next one. What's I hat cross j hat? Well, let's get the magnitude first. The magnitude of the answer, the magnitude of one times the magnitude of the other times the sine of the angle between them. Okay, now the magnitudes are one again, like the unit vector's magnitude is one, the other unit vector's magnitude is always one. The angle between them is 90 degrees now. How do I know? Because these are the two base, these are two of the three base unit vectors. I is defined to point along the x-axis, wherever your x-axis is. And J is defined to point along the y-axis. I don't care where your x-axis is. Your y-axis, by definition, has to be perpendicular to it. Again, that's like the point of the inclined plane example that I put in the classroom. So the angle is 90 degrees. So the magnitude of this cross product, I hat cross j hat, the magnitude is 1 times 1 times 1, which is 1. Now that's the magnitude of the answer. So if you put 1 as your answer, you're on the right track. You're doing something correct. But that's not the full answer because this isn't a dot product. This is a cross product. We're looking for a vector as an answer. So we would do the right-hand rule, in effect, to get the direction of the answer. The direction of the answer has to point perpendicularly to both of the original vectors. The original vectors are along the x-axis and the y-axis. So the answer has to point along the z-axis. The unit vector that points along the z-axis is called k hat. So the answer to this question technically would be 1 times k hat, i.e. k hat. The direction is along the z-axis. The magnitude is 1. That is a vector called k hat. So from now on, I know we have 2 minutes, but that was an exercise for practice, but it's a concept now. From now on, if you cross the I hat vector with the j hat vector, you get what is known as the k hat vector. And then similarly, if you did, that's right-hand rule. If you cross I with j, you get k. Or if you cross I with j, you get k. Same thing. Similarly, my right hand rotates. If I cross j with k, I get I. If I cross the y-axis with the z-axis, I get the x-axis. It goes round and round like that. So then, for the last question, we have 1.5 minutes. What would I cross k be? Well, I don't know. What's x cross with z? Am I supposed to stick my thumb through my palm? What? Well, I don't know, but I know this. I know k cross I just said was j. I cross j is k. K cross I is j. It just wraps around like that, if you think about it. So k cross I is j hat. Therefore, since the operation's anti-commutative, I cross k must be negative j hat, etc. So that's the sum of how okay? So that's how all of the unit vectors work in dot products and cross products. From my understanding, correct me if I'm wrong, I hat would equal to what? No. I is for x, j is for y, and k is for z. So almost what you said in the direct chat, but not quite. Okay, wait, so that's all right. We'll leave it there for now. And I'm gonna upload the same PDF, but sorry. Wait, can I go back to the last well, it's 10:40. Yeah, hang on. So someone's asked, I'm gonna, you go all have to go. I'm gonna stop. You can go, but someone's asking me to re-explain the last thing, which I'm happy to do for any of you who wants to stay. And I feel like therefore I'm going to leave on the recording at least right now because it might help other people. So you can go because it's 10:40. But the person who just asked, hang on one second. And I'll right. So the last question. So the last question was, what is I cross K? That sounds, have a good day. Yes, thank you. That sounds harder because it sounds like I'm skipping a vector or something like that. But the key insight is the right hand rule works for any of these, right? If you understand that that X cross Y gives you Z, well, similarly, Y cross Z would give you X. Like it just keeps your right hand can just keep rotating around. Um, so I cross J equals K hat. Stop me if and again, maybe I'll turn off the recording in a second if it helps if you want to ask. But I hat cross J hat equals K hat, definitely. Therefore, J hat cross K hat equals I hat. Like, and this is like always now. I'm saying and J hat cross K hat, did I just say that equals I hat? I might have just said, and sorry, and K hat, it just goes round and round and round forever like that. So K cross I equals J. K cross I equals J, middle of the page. But then the key but, what we said 2 days ago, if you think about how your right hand works, the cross product is anti-commutative. If you flip the order that you're doing, if you do B cross A instead of A cross B, you get a negative sign in your answer. Like you don't get the same thing if you go forwards or backwards. Forwards and backwards are negatives of each other. So if K cross I hat equals J hat, then that means that I hat cross K hat equals J hat. Like, what does that mean in English? It means if there's a vector that points along the x-axis and a vector that points along the z-axis, and I cross the x-axis into the z-axis, I get an answer that points negatively along the y-axis, like that points back along the y-axis rather than out front on the y-axis. Does that make sense? Okay, wait. Hold on. And there's okay, good, great. Thank you. And thank you for hanging in for the 5 minutes to ask that. Okay, great. So that's you person. And now I'm looking in the chat. I think I'm gonna leave this recording on as long as I'm just the one talking about concepts. I'm just doing a sort of like the chat. Oh, that's interesting. Okay, one of you is saying in the chat, this is fascinating. One of you saying, is this kind of like sine squared of theta plus cosine squared theta equals 1? That's a really good connection. That's a really good connection because, oh, it's just you now. Okay, wait. I'm going to wait, I'm going to turn off the recording. It's just you, so I'm going to talk, but I will turn off the recording.